Hi there. Welcome to Labster. Today you will learn about atoms, ions, and isotopes. Are you ready to explore the subatomic world? This simulation uses using the lab pad is an important way to perfect. Then let's get started. Find a lab coat and pick it up. Find a glove box and click on it to put on the gloves. Did you know that all matter is made of atoms? Yes, even you. The atom is the smallest unit of matter that retains its chemical properties. There are many kinds of atoms with different properties, and we call each of those types an element. Your body is mainly made up of atoms of the elements hydrogen, carbon, nitrogen, and oxygen. As for me, I am almost pure carbon and iron. Would you like to know some more facts about the atom? The theories about atoms are as old as ancient Greece, but different models have been studied over the past few years. I tried to summarize the great influencers of the atomic theory. Check out the image or click the View Image button. In order to understand how small an atom might be, compare it to a coin, and then think about how small a coin is compared to Earth. Check out the image or click the View Image button. Since you now have an idea about the size of an atom, you realize that I am not going to read all these zeros for you. Check out the image or click the View Image button. Even if you haven't heard of them, atoms consist of subatomic particles, neutrons, protons, and electrons. As your height and weight may be used to describe you, the same way, the number of subatomic particles is used to identify atoms. Check out the image or click the View Image button. You seem eager to start exploring. I like that. We are going to learn so much about the atomic structure together. Enter the lab. Welcome to the Atomic Structure Lab. In front of you, you can see the periodic table of the elements, where all the known elements are listed. Have a look at it and then head left to the hollow table. This is Labster's atom building hollow table. Here, you can visualize the structure of atoms and build atoms with your own hands. Atoms consist of a heavy nucleus made of neutrons and protons and surrounded by lighter electrons. Let's introduce each of the subatomic particles one by one and place them in the atom. Pick the subatomic particle and place it in the atom. First, pick up the neutron from the hollow table and place it in the nucleus. Neutrons are the heaviest subatomic particles. They live in the nucleus of the atom, and they have no electrical charge. Now, add a proton to the nucleus. Protons are almost as heavy as the neutron, but not quite as much. Together with neutrons, they make up the nucleus of the atom. They have a positive electrical charge. Put the electron in orbit around the nucleus. Electrons orbit the nucleus, but they are not part of it. They are the lightest subatomic particle, almost 2,000 times lighter than protons. An electron has as much electrical charge as a proton, but the electron's charge is negative, while the proton's charge is positive. Since most atoms in nature have the same number of protons and electrons, atoms are, in general, electrically neutral. Click on the red button to submit your answer. You have in front of you a lithium atom. This atom has 3 protons and 4 neutrons in its nucleus, and 3 electrons around the nucleus. What are the subatomic particles of an atom? You can lower your lab pad and use the lithium structure on the hollow table to help you. Not quite. Click on the View Image button to see a diagram of the components of an atom, or on the View Theory button for more information. Alternatively, hover over the different elements of the lithium atom in the hollow table. Well done! An atom is made of protons and neutrons in the nucleus and electrons around the nucleus. Click on the right arrow of the screen of your hollow table. To describe an atom briefly but in detail, scientists use nuclear symbols. A nuclear symbol has 4 parts. First, the atomic number, which tells you how many protons the atom has. Second, the mass number, which tells you the sum of the number of protons and the number of neutrons. Third, the charge number, which tells you the difference between the number of protons and the number of electrons. Finally, the chemical symbol, the symbol of the chemical element of the atom. If 2 atoms have the same atomic number, they are from the same element. Create a neutral atom with an atomic number equal to 2. Do not worry about the mass number for now, I will help with that. Click the red button once you are done. Almost done. You got the atomic number right, but remember the atom needs to be neutral. That means that the charge number should be 0, or rather, that there should be as many electrons as there is protons. You did it! I placed 2 neutrons in the nucleus to make the atom stable. Behold the mighty atom of helium. An atom where the atomic number is equal to 2 means that there are 2 protons in the nucleus. Because the charge is neutral, there should also be 2 electrons. The mass number is the total number of protons and neutrons in an atom. For this atom, the mass number is 4, because we have 2 protons and 2 neutrons. Click on the right arrow of the hollow table to move to the next setup. Create an atom with mass number equal to 3 and neutral charge. Click the red button when done. Good job! An atom with mass number equal to 3 has a total of 3 protons and neutrons in its nucleus. In this case, there should be 2 protons and 1 neutron, 1 proton and 2 neutrons, or 3 protons present in the nucleus. Since the charge is neutral, there should be as many electrons as there are protons. Now let us have a look at ions. Although in nature most atoms have as many electrons as protons, it is possible for an atom to lose or gain electrons. When an atom has different numbers of protons and electrons, we call it an ion. When an atom loses electrons, its charge becomes positive and we call it a cation. When an atom gains electrons, its charge becomes negative and we call it an anion. Click on the right arrow of your hollow table to move to the next setup. Create a cation. Click the red button once you are finished. Try changing the number of electrons that orbit the nucleus. Try changing the number of electrons. You have made such a positive impression on me. A cation is positively charged, meaning that the number of protons should be larger than the number of electrons. There is just one more concept you should get comfortable with regarding the atomic structure: isotopes. Atoms with the same number of protons but different numbers of neutrons are isotopes. Since they have the same number of protons, they have the same atomic number and they belong to the same element, but they have different mass numbers. Are the following atoms isotopes of the same element? You can click the View Image button to view the image. No, this is incorrect. Remember that isotopes of the same element have the same atomic number, but a different mass number. Have another look at the image and compare the atomic and mass numbers of the two atoms in it. Click. Exactly. The two atoms above do not have the same number of protons in their nucleus, which means that they don't have the same atomic number. Since their atomic number differs, they are not isotopes of the same element. When dealing with isotopes, it is important to keep the atomic number in mind. What is the atomic number of lithium? Check the structure of the lithium atom on the hollow table to find out. Careful. Remember the definition of atomic number. Now, what would it mean for the lithium atom in particular? Remember there is a model of the lithium atom on the hollow table. You can also click on the View Theory button for a refresher. You are right. The atomic number is, by definition, equal to the number of protons in the nucleus. Which of the following represents an isotope of lithium? You can use the hollow table to help you. Not quite. Remember your answer to the last quiz question and the definition of an isotope. Do isotopes of the same element always have the same atomic number? What about the Correct. In nuclide symbol notation, the top number reflects the number of both neutrons and protons, and the bottom number reflects the number of protons. Because isotopes of the same element always have the same atomic number, they can differ only in their mass number, reflecting the different numbers of neutrons in their nucleus. In this case, the lithium atom has only one neutron. Create an isotope. Click the red button when you are done. Good job. Now make this isotope an anion. In a real chemistry lab, an anion of lithium may be hard to come by, but, in a virtual simulation, it is a click away. Isotopes are important for understanding the evolution of other planets. For example, the different patterns of xenon and krypton isotopes on the surface of Mars give valuable insights to scientists investigating the reactions occurring in the crust of the planet. Amazing work! You've become a real expert on the atomic structure. You know what? I think you are ready to use your knowledge of atoms, ions, and isotopes. Are you ready to teleport to the alien planet? Hold on fast to your lab pad and take a deep breath. I am teleporting us to the alien planet. Behold the beautiful yet eerie scenery of this exoplanet. In this hostile environment, the Labster rover is on a mission to determine if this planet is, or was, suitable for life. The rover's robotic arm can pick up rock samples. Click on the rover. Now it is time to pick up some rock samples. Click on the rock samples in front of you. Good job. Let me teleport both you and your sample back to the lab. We have Go to the workbench. Leave your rock samples in the bowl. Let's have a look at the atoms of the alien rocks. I will perform a quick analysis with you to identify the elements present in the samples. Across from your workbench there is the periodic table. It contains all the info you need to identify the atoms from the samples. Move closer to the periodic table. I identified an element with atomic number equal to 6 in the samples you brought back. What element is it? You can find it in the periodic table. Are you sure? The number of protons in an atom is its atomic number. The number that you can see in each of the elements of the periodic table is its atomic number, so the elements appear in order of their atomic number in the periodic table. What is the sixth element of the periodic table? Check out the View Theory button to know more. Amazing! Elements appear in order of their atomic number in the periodic table when reading left to right and up to down, so an atom with 6 protons corresponds to the element of carbon. This is very interesting. Carbon is one of the main elements that make up organic life on Earth, so we would expect to find it on any planet capable of sustaining life. We have found 2 isotopes of carbon in our samples, the first with mass number 14 and the second with mass number 12. How many neutrons are in each of the isotopes? No, this is incorrect. The mass number of an atom is the total number of protons and neutrons in its nucleus. From your last answer, we know that carbon has 6 protons. For more information, click on the View. Good thinking. The mass number is the total number of protons and neutrons. Since we know from the last question that carbon has 6 protons, an isotope of carbon with mass number 14 must have 8 neutrons, while an isotope with mass number 12 must have 6 neutrons. We can use isotope abundances to estimate the age of rocks. The abundance of the isotope of carbon with mass number 14 suggests this rock formed very recently, so maybe life existed very recently on this planet. The second element I identified has 26 protons but only 23 electrons. Can you tell me the name of it after consulting the periodic table? That's right. There are more protons than electrons, so the total charge is positive and the atom must be a cation of iron. Cations of iron like this one are common in oxygen-rich environments, so the fact that we found this cation points to an oxygen-rich atmosphere suitable for life. It would also explain why you didn't have any issues breathing on that planet. Nice job! You discovered that there was carbon and oxidized iron in the samples you brought back from the exoplanet, among other unidentified elements. This all points in the right direction for the habitability of the planet. There is just one more experiment I'd like to perform. Go to the workbench. Pick up the pipette. Click on the beaker to get a few drops of the acetic acid. Click on one of the white rocks to add the drops on them. Leave the pipette on the stand. There is some gas coming out of your white rocks. It looks like a reaction is taking place. The acid just released carbon dioxide gas. This means that the white rock contains carbonates. Carbonates naturally form in the presence of carbon dioxide and liquid water, so they could provide important evidence of the presence of liquid water in the exoplanet. The abundance of carbon, the oxidation of iron, and the presence of carbonates in these rocks provide valuable information. They hint at the presence of organic molecules, water, and oxygen, all of them very important for life as we know it. I would say we have a good reason to prepare for another trip. Ready for another trip to the exoplanet? We were right. There is life on this planet. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback.